Hello everyone, I'm Kevin Kupczynski, planetarium and STEM educator at the Springfield Science Museum. We hope you come to visit the museum sometime soon, and we especially look forward to seeing you in our planetarium when it reopens. Meanwhile, please enjoy this astronomy video. In this video, we're going to get an idea of how different the sizes of stars really are. We're going to use pictures from a program called Celestia to help us. Celestia lets us pretend we are flying around in the galaxy. We are going to use it to pretend to visit other stars. First, though, let's learn more about stars. All stars, including our sun, are giant balls of gas and turn one kind of gas into another. They turn hydrogen into helium by nuclear fusion. That's what makes them bright and hot. Some stars are big balls of gas, some are small. The small ones are dim and cooler, big ones are bright and hot. We'll learn about temperatures and colors of stars in a different video. Right now, we'll think about size. A couple of astronomers named Hertzsprung and Russell wondered what would happen if they took the measurements of the temperature and brightness of a lot of stars and plotted those results on a graph. Now, if there was no relationship between the temperature and the brightness, the stars would be scattered all over the graph. Instead, they found the pattern we see here. This graph is now known as the Hertzsprung-Russell or HR diagram. Looking at the graph, we see that the combination of brightness and color puts stars into three major groups. The biggest group starts at the upper left of the chart and goes down across the diagonal to the lower right. This is called the main sequence. Most of the stars we see in our sky are in this group. We also see these other areas, one that is labeled supergiants and another labeled white dwarfs, and a little bit of a bump out of the main sequence called the giants. We see the position of our sun in this diagram pretty much in the middle of the chart. It is medium brightness and medium temperature. Giants and supergiants have used up about all of their hydrogen. They use helium and other elements, but they are not as hot when they do this, so they become cooler in temperature, which means they are redder. When they get to this stage, they also expand in size. This giant size makes them look very bright in our night sky. The white dwarfs are what's left over after a giant star explodes. They are hot, but they are very small, so they are very dim. Now let's go on our tour of the stars. This picture shows us what the size of the sun looks like from our Earth. The distance between the Earth and the sun is called 1 astronomical unit. So that's how far away from the sun we are right now. We're going to compare this to other stars by seeing what they look like at the same distance, 1 astronomical unit. Let's start with one of the giant stars. This one is called Aldebaran. We are 1 astronomical unit away. Just to remind you, here's the sun at 1 astronomical unit, and now here's Aldebaran again. Whoa, that's a big difference. And this is just a giant. What about a supergiant? This supergiant is Betelgeuse, and we've got a problem. Supergiant stars are hundreds of times bigger than our sun, so that means they are bigger than 1 astronomical unit. Distances are measured from the center of one object to the center of the other. So if we get to 1 astronomical unit from the center of the star, we would be inside of it. If we want to get a look at the whole star at once, we'll have to back off to about 9 astronomical units. In our solar system, Saturn is about 9 astronomical units from the sun. So big stars are really big. What about small stars? Let's try one of those. This is Proxima Centauri, the closest star to our sun. It is a red dwarf, one of the stars at the bottom right of the main sequence. You might be thinking that it doesn't look too much smaller than the sun, but we had to come way closer than 1 astronomical unit to get a good look at it. In fact, we are about 7 times closer to this star than Mercury is to our sun. We need to back off to get to 1 astronomical unit. Keep your eye on it. Here we are 1 astronomical unit away from a red dwarf. Even though it is the closest star to our sun, we cannot see it from Earth without a telescope, because back on Earth, we are several 100,000 astronomical units away from Proxima Centauri. Let's finish up with a white dwarf. This one is called Sirius B since it orbits the star Sirius. Sirius is also known as the dog star, so Sirius B is sometimes called the pup. This star is only about the size of our Earth. Again, we are way too close so you can get a good look at it. Keep your eye on it as we back off to 1 astronomical unit. Can you still see it? White dwarfs are also too small and too dim to be seen from the Earth without a telescope. So now you see that stars come in quite a variety of sizes. Unfortunately, it is hard for us to see those sizes when we go outside to look at the night sky. We are just too far away. Perhaps the next time you go out and look at the stars, you'll remember the images you saw in this video and imagine the variety of stars as you enjoy the beautiful night sky. I hope you get a chance to do that soon. We'd also love to see you here visiting the Springfield Museums someday. If you like astronomy, check out our website for the Stars Over Springfield event, and you might even consider joining the Springfield Stars Club. Thanks for listening.